Have you ever puzzled over how quantum mechanics describes reality, especially when it comes to something as fundamental as observation? It seems like simply looking at a particle can change its very nature, a concept that has baffled brilliant minds for decades. In relational quantum mechanics, or RQM, the concept of a universal wave function collapse as an objective event, independent of any observer, is not considered real. Instead, RQM redefines what real means in a quantum context, shifting our understanding of how observations impact physical systems. The core reason for this unique perspective lies in RQM's fundamental premise. Quantum states are not absolute properties of a system but are always defined relative to an observer. What one observer measures as a collapsed state, say a particle spin being up, another observer who has not interacted with the first system might describe as the first observer and the particle being in a superposition. This means that quantum states are descriptions of the correlations or relationships between systems, not intrinsic features of any single system alone. The collapse is then seen as a relative event, happening only from the perspective of the interacting observer, not as a global, instantaneous physical process. So, how does this change our understanding of quantum events? It encourages us to think about quantum mechanics not as describing things as they are, but as describing things as they are seen or as they relate to an observing system. For instance, if you measure a quantum system, its state collapses for you. But for someone else who has yet to interact with your measurement device, your entire system, including you and the particle, is still evolving unitarily as one large superposition. This forces us to consider the reference frame of the observer as an integral part of the quantum description. A fascinating insight from RQM is its natural resolution of Wigner's friend paradox, which highlights this observer-dependent reality. From Wigner's friend's perspective inside the lab, the quantum state collapses upon measurement. But from Wigner's perspective outside the lab, until he measures the friend's state, the friend and the measured system remains in a superposition. RQM embraces this relative truth, stating both perspectives are valid within their respective relational contexts. This view also aligns with the no communication theorem, ensuring that no information can travel faster than the speed of light. Ultimately, understanding relational quantum mechanics helps us appreciate that the quantum world might be less about objective properties and more about the intricate web of relationships. It provides a consistent framework for handling observer dependence, making quantum theory internally coherent and offering a fresh lens through which to view the mysterious process of quantum measurement.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.